In my last video, which is linked in the description, I represented the frictional losses in a bicycle chain through the Coulomb friction model that you can see here. In this video, I'm going to talk in general terms about the forces in the chain and how they relate to frictional inefficiency and chain wear. Before I go any further, I'll just alert you to a recent GCN video looking at the same subject that I'm covering. That is bicycle chain efficiency, friction and wear. However, there is a major error in that video. It is GCN after all. Let me know in the comments if you've identified it. Let's get back to my analysis. Take a chain just like this one on a bicycle and we apply a force, let's call it PF for pedaling force. Then in order to maintain Newton's third law, every action has an equal and opposite reaction. We have to apply the same force at the other end of the chain. All of the links in that section of the chain are subject to the pedaling force. That pedaling force is applied via the chain wheel to the roller, and then it's passed on to the inner links through the pin to the outer links and then to the next pin, etc. In order that the chain can transmit those forces, the materials and the contacts are in a state of stress. That stress state is defined by a force per unit area, and if the stress state goes too high, the materials or the contacts will break down and the chain can fail. Don't worry, the chain is not likely to snap, as I'll show in a future video. However, the forces acting through the chain can be important where the different parts contact each other. The regions of the chain where friction and wear is most prevalent is shown in this picture. That's because those are the regions of the chain where both forces and movement occur. If you remember from the last video, in order to develop friction and wear, you need both those forces and the relative movement. Only wear in the orange regions will cause the distance between the pins to change, and that change in distance between the pins is often called chain stretch, although strictly speaking, the chain isn't stretching. The areas marked red in the diagram will wear, but they won't cause the distance between the pins to change. I now need to move on to the concept of work done. In this case, the work done relates to the frictional losses in the chain. In classical mechanics, the work done is the product of the force and the distance through which that force moves. Or in rotational terms, the product of the frictional torque and the angle through which that frictional torque moves. As the chain is used, work is done by the frictional forces and the movement of that chain, and those are the frictional losses that the chain absorbs. It's those frictional losses that we want to minimize. In order to reduce the work done, we can implement a strategy of reducing the force, reducing the movement, or a combination of the two. And those are the strategies I'm going to outline in future videos. I've already alluded to a uniform pedaling force within the chain. However, the forces that act on the chain are not necessarily uniform. In the next video, I'll talk in more detail about the different types of frictional force that occur within the chain. I'll also relate those forces to the relative movements within the chain, and that's where the work will be done. Or alternatively, that's where the friction and wear will occur. That will allow us to target our friction and wear reduction strategies. If you want to see the earlier videos, then follow the links in the description. If you want to see the future videos, then subscribe to the channel and click on the bell icon for notifications. From me until the next video, it's goodbye.